The following program is brought to you by Caltech.
Welcome back. Last time we talked about 3 learning principles that if you are in the business of machine learning, you should be aware of in order to avoid the very common pitfalls in applying machine learning. The first one is Occam's razor, which says simpler is better, and better in terms of the performance. And therefore, you should use a razor in order to trim the explanation of the data, the hypothesis or the complexity of the hypothesis set in this case, in order to get to the bare minimum that is consistent with the data that you have. Now, in making this a specific statement that is justified, we had simply 2 arguments that are interesting in their own right. One of them is the fact that a complexity of an object corresponds to the complexity of a class of objects. So this correspondence was one. The other one is that if you have an unlikely event, then when it does happen, that is more significant than it was a likely event to begin with. And when we put them together, we get the proofs of Occam's razor under different assumptions. The second principle had to do with sampling bias, which reminds you of the fact that we said that the training data comes from the same distribution as the test data. That was the basic assumption in all of our theoretical analysis. And when it doesn't, then there is a bias. And since your learning algorithm learns only from the training data, it is going to inherit whatever it is that is in the training data as a distribution, and therefore the result will be accordingly biased. If the mismatch is sort of nice and continuous, at least non-zero for all the points, then there is a way to compensate for the sampling bias by trying to make the sample look as if it was coming from the other distribution. But if the training data doesn't represent a particular part of the space, so that space has a probability 0 as far as the training is concerned, but it has a positive probability for the test, then there is really nothing that can be done to replicate the behavior of the target function over that part of the space, and therefore you get something that is inherently biased. The last principle had to do with data snooping, which is the most important in terms of there being a trap that you fall into. And the idea here is that when you use a data set in the training, in any capacity, it could be very light capacity, and we saw an example where the only way the data was used was in order to derive normalization constants for the inputs, something very light. Nonetheless, the fact that you use the data means that you cannot call it test set after that and trust the performance that is suggested by that data set. And indeed, we took a case where we allowed snooping, and we ended up with a very optimistic view, when in reality, the performance was very poor. And of course, if you go for the real out of sample, you hand the system to your customer, and they test it, they will see the real out of sample, not the optimistic performance that you had. Today's lecture is the final lecture, and I am going to use it in order to give the big picture of machine learning and try to fit the stuff that we covered within the big picture, and then tie up a couple of loose ends that are relevant to that. Okay, so here is the outline. First, I'm going to talk about the map of machine learning, because machine learning is pretty diverse, as you will see, okay? And we will see what we covered and how you can pursue it further, and what topics I would recommend that you read about and what not. And then we will take 2 topics. I will explain why we picked these 2 topics, and talk about them in some detail, not in very technical detail like we cover the topics of this course, but at least to give you some background about where these topics stand as far as the machine learning is concerned, so that if you decide to pursue them, you have a head start. And finally, I'm going to acknowledge the people who have contributed greatly to this course. Okay. Well, when it comes to machine learning, it's a jungle out there. And it's interesting that if you buy 2 books on machine learning and you look at them, you will feel that you are reading about 2 completely different subjects. If one of them is theoretical and particular theories, there are a bunch of theories, and one of them is practical, or one of them is emphasizing a particular technique, they just have nothing in common, not even the jargon, okay? So if you go out on your own and just look at what happens in machine learning, pretty much this is the picture you will get. Okay. Not a pretty picture, okay? And you can see buzzwords galore, and people will get excited about one thing and tell you that this is God's gift to humanity, and the other thing, people will be very opinionated. It's just all over the place. So I'm not going to attempt to be complete, okay? Because being complete here is fatal. Trying to cover everything so that everybody is happy that you covered the results they got, I don't think this is a good strategy. I preached the Occam's razor last time. Remember Occam's razor? Okay, you should have a razor, and then you should trim until you get the essential part. This is pretty much what I try to do here, okay? Because I believe that if you understand the fundamentals inside out, you can pursue things completely on your own, okay? From then on. You are not going to be intimidated by grandiose statements or of one nature or another. You will know where things lie and whatnot. So my task was to get the foundation right, okay? And in the course of doing that, I had to omit many topics, okay? So now I'm going to give you the map of the whole thing, what we covered and what can be pursued in order just to have a good outlook on the situation. Okay, so here is the map. There is theory, okay? And theory means that you mathematically model what happens in reality and then try to do mathematical derivation in order to arrive at results that are not otherwise obvious. That's what theory is in general, okay? And there are usually two aspects when you look at a theory: what assumptions they made, and then what the derivation is in order to get to the results. I hardly ever saw a situation where there is a problem with the second part. People are very competent mathematicians. They are not going to make a mistake in derivation. So the chances are they will, when they make a statement mathematically, they actually mean it and they proved it. So that is not our concern. The biggest pitfall in theory is that people make assumptions that make what they are solving really divorced from the practice that you are going to see when you use machine learning, okay? And when I picked the theory, I picked it with a view to relevance to practice. I wanted to get something. It has to obviously be mathematics and it has to be proved and all of that. But then when you see the result, you can use it. And I will go through other alternatives that have succeeded in that to different degrees. Then there are techniques. And that is really the bulk of machine learning, okay? We covered some techniques, but I'm going to categorize techniques into two sets and give you samples, and then you will understand from what we have done where it lies and how you can pursue it further. And finally, there are paradigms. And paradigms meaning different assumptions about the learning situation, not mathematical assumptions, but different assumptions that deal with different learning situations, like, for example, supervised learning versus reinforcement learning and whatnot. And when you make these assumptions, the problems you are solving are sufficiently different that you end up with really a different body of knowledge that you have to study, and therefore we call them different paradigms. Okay? So these are basically the categories. So let me start with the paradigms first, because it's the higher level, and then go to the other ones. Okay. So we covered supervised learning. That was almost the exclusive topic of the course, and it is by far the most popular and the most useful form of machine learning. So if you cover just that, you are already very much ahead. The other topics are interesting and they have applications and they should be studied, okay? But definitely not in the league of supervised learning in terms of impact on practice. We touched on unsupervised learning with a single algorithm we had, but we at least got the idea that clustering is the key, and indeed clustering is the key. And with unsupervised, there are also variations of that. There are semi-supervised, and there are everything I say here has a bunch of variations already there. So I'm just giving you the center of mass of these paradigms. Then there is reinforcement learning that I described in the first lecture very briefly, but we didn't cover at all. And the reason is justified, because the main problem in supervised learning was the question of information. Do I have enough information in the data in order to get the target function and generalize, right? When you go to reinforcement learning, remember what reinforcement learning was. You don't have the target value on the examples. You just take an action, okay, which is an output, not necessarily the target output, and then something comes that tells you that you did well or you didn't do well. So the sort of reinforcement of good actions and elimination of bad actions will make you eventually converge to a good solution. And we said that it applies to games. Let's say you're playing, trying to learn backgammon. And what you do, you just play against yourself, generating at will examples as you want. Here's a situation, what do? I'll do something. I can generate that. The only question is, after you do that, how do you take the feedback of winning and losing and go back and adjust your strategy such that you converge to a good strategy? So the issue here is completely different from supervised learning. It's not a question of information, it's a question of the algorithm that will take all of these tons of examples that you can generate at will and produce a way to converge to a solution from one strategy to a better strategy to a better strategy. So it's a completely different paradigm. And if there is one topic in this entire view graph that I would encourage you to pursue, would be read about reinforcement learning. It's a very sweet subject. Okay? Finally, there are many paradigms. Active learning. So active learning, it could be active reinforcement or active supervised. Active learning means that instead of someone giving you the data set, you query about the value at a particular point. So you give me the input and you ask for the output if it's supervised, or you give me the input and expect a reward or punishment if it's reinforcement learning. Okay? So it's an adjustment, and there are some interesting results there. And the other sort of mini paradigm is online learning, and this is purely computational consideration. Okay? So take any form of learning, and instead of giving you the full data set and allowing you to work with it any way you want, I'm streaming the data set to you. So you take something and you try to modify your current hypothesis, and then you take the other guy, and you cannot store everything. If you could store everything, you have the whole data set. So there are limitations on storage and computation, and under those constraints, you ask yourself, how can I learn, and how close can I get to the optimal as if I had the whole data set and whatnot. Okay, so these are the most famous paradigms. There are other paradigms. I'm not trying to be exhaustive here. Now let's go for the theory. Okay, the main theory in machine learning is the Vapnik-Chervonenkis theory. And it is the one that I covered in great detail in this course, as you realized. Okay, and the reason is very straightforward. It's relevant. Okay, you do the math, you go through the proofs, and then you get the VC dimension. You equate it to the number of parameters in some cases. And when you go to practice, even if you are taking bounds and treating them as if they were equalities, that leap of faith works very well in practice. So it's not that the theory was there and we decided that this is a good one. The theory was there, and then we tried to take wisdom from the theory and apply it in practice, and it worked. This is the value added by choosing a topic and putting it here. You know that there is a reason why it's here, and the reason here is that it is actually relevant to practice. Then there is the bias variance. Well, bias variance is sort of a sweet little theory, and it gave us some intuition about this. And indeed, it was included. It was sort of low cost to include it, and it does lead to some understandings like the learning curves and whatnot. There are theories that I didn't describe, although that they are very substantial in the literature. One of them is based on computational complexity. It basically treats machine learning as a branch of computational complexity with an emphasis on asymptotic results. So there's a question of, can I do this in polynomial time or not? And it's a very respectable body of work. And the only question for including it or not including it is whether these particular results correspond to something that I face in practice. Okay? So when I look at it, should I do the computational complexity part of it, or should I do the generalization part of it? The generalization part of it won hands down, because it's the one that is the bottleneck when I practice machine learning. And finally, there is the famous Bayesian approach. Now, this treats machine learning as a branch of probability. Okay? So you have a problem, we can always put a probability distribution, and by the time you put the full joint probability distribution, you can answer all questions. Okay? And it's a very sweet theory, because you can sort of ask any question you want, and you will find a very concrete, rigorous mathematical answer to that question if you have the setup of the joint probability distribution. Okay? Okay, so now let's go for the techniques. I mean, there are other theories again. I just give you the biggest players. When you look at techniques, you should separate models, as in hypothesis sets and algorithms that go with them. That's one category. And then the high-level methods like regularization, for example, that doesn't restrict itself to a particular model, but is superimposed on anything you use. Okay, so I will look at members of those categories. So we looked at the models. Linear, we emphasized a lot. It is not usually emphasized in regular machine learning courses. They usually go for other models. It's emphasized very much in statistics, for example. And I find it to be very underrepresented in machine learning. It's a very important model. With the nonlinear transform, you can cover a lot of territory, and it's very low cost, and it should be tried in many learning problems. Then we went on to neural networks. You have seen that. Support vector machines and the kernel methods. Okay, so we covered quite a bit of territory. Nearest neighbors, I alluded to very quickly when I talked about RBF. It's a very standard method. Not much to say about it, except that it's a good benchmark. That if you have a data set, why don't you categorize everything according to the nearest neighbor? And this will give you a performance, and then you can compare other methods to that. It's not that difficult to implement. We looked at RBF and its relation to many things in machine learning. And then there is Gaussian processes, which some people are completely fond of, which is great. And it really has the same spirit of Bayesian. It's a full probability distribution. So a process here means a random process. A random process is nothing but a random function. If a random variable is a random number, a random process is a random function. Okay, so you have probability distribution over different functions that can come out. Okay, and the assumption here is that they are Gaussian, which means that if you take any finite number of points, the probability distribution of the y-coordinate is jointly Gaussian for those guys. Okay? So if you have a full description of that probability distribution, you can solve anything you want, because you can say, okay, if I have this data point, then I am conditioning on that Gaussian variable being equal to that, and I'm asking myself, what is now the conditional distribution of the other guys? And for Gaussian, this is completely solved, and you have nice matrices to just multiply out and get that solution. So it's very good to use, and if you are modeling something that happens to be a Gaussian process, okay, then obviously you win greatly, because you are actually matching that. Okay. There's SVD, which is the singular value decomposition, used figuratively in this case. This is the factor analysis we used in the Netflix problem, where we represented the user as a bunch of factors and the movie as a bunch of factors, and we try to match. When you put this, you find that it's as if you are decomposing the ratings matrix, the entire rating matrix, into two matrices, and this will be similar to singular value decomposition in mathematics. So we have seen part of that. Finally, there's graphical models, and graphical models is almost a different paradigm in its own right. Okay. What are graphical models? They are a model for where the target is a joint probability distribution. That's what you're trying to learn. Okay, and the key here is that the joint probability distribution between a very large number of variables becomes very difficult to manage computationally, because there is, the number of possibilities would be exponential in the number of variables. So the bulk of work in graphical models is trying to find a simple way or an efficient way in order to get answers about that joint probability distribution and to learn it. So it is mostly computational, and it's based on graph algorithms. And the main aspect of putting it in a graph is to use the properties that happen to be conditional independence as a way to simplify the graph. Okay? So if you look at the things I showed so far, probably there would be a full course in graphical models, which is completely justified. If you are in the business of modeling joint probability distributions and computation is a consideration, this is the thing to learn. There is no question about that. Okay? It's specialized, but it's very helpful in that case. Okay? And the other one I mentioned with reinforcement learning, usually taught together with active learning, because there are a lot of commonalities. Now we go for the methods, and the methods are very important because they cover a lot of territory regardless of the model you have. We use regularization. Can you think of other methods at the same level that we used? Regularization, and we used validation, right? These were all methods overall, okay? There are things we didn't cover, and one of them is aggregation, okay? Putting together different solutions. And the last one we didn't cover was input processing. This is something you do regardless of the model you are going to use. And I find that input processing is best taught within a projects course. It's a very practical matter. And when you teach a projects course and people will have to deal with the real data, it's a good thing to start by telling them, okay, here is the principal component analysis in order to normalize and decorrelate the inputs and whatnot, and this is the value, and then they can try. There is sort of little intellectual value to input processing. It's a practical matter, and therefore it is best taught when you are teaching a practical course. Okay, so now from all of this, I am going to talk about two topics today, okay? Okay, so one of them is Bayesian and the other one is aggregation, okay? I'm not going to talk about them in depth. I'm actually going to try to make a point, particularly about Bayesian, okay? And you say we just told us about this, the razor, and you trimmed it and you got the solution right. Why are you now adding up stuff to the minimal possible? There is a good reason. The Bayesian is the elephant in the room, okay? If I don't talk about it, you will hear about it a lot, and you will wonder, why in the world didn't I talk about it? It looks great when you look at the results, okay? So I need to put it in perspective, and that's what I'm going to try to do. I'm not going to cover the scope of Bayesian. I'm going to cover the foundations of the Bayesian approach and make a point about, when is it valid, when can you use it, what are the drawbacks, and what not. The other one is aggregation. I would say that aggregation was the runner-up topic in this course, okay? I would have normally included it, okay? If I had more time and I had a natural position for it. Because it's a fairly simple technique and covers a lot of territory and has been successful. So I'm going to try to cover it in some level of detail that will make you at least able to read it and understand what you are reading and where it lies. Okay, so this is the plan. So with that, let's go to the two topics. Bayesian learning first, and then I'm going to go about aggregation methods. Okay. Bayesian learning is trying to get a full probabilistic approach to learning. So the first thing to do is to remind you of the learning diagram. Let me magnify it a little bit. So we are not going to go through the details of it. We are just going to concentrate on the probabilistic aspect. Okay, there are many probabilistic components. One of them is inherent, which is the fact that the target could be noisy, and therefore we model the target not as a function, but as a probability distribution. Okay? Think of the case, for example, we dealt with as trying to predict heart attacks. Okay? Getting a heart attack or not getting a heart attack is a probabilistic aspect. And if we have our target as the probability of getting a heart attack given certain conditions within a certain amount of time, then the examples I'm going to give you don't give you that value of the target function, but give you realizations from that probability distribution that are noisy. And therefore, I give you that probability distribution P of y given x. So that one is sort of built in terms of the functions or the noisy functions we are trying to learn. The other probability distribution we had was the input probability distribution, and that was admittedly an artificial addition to the problem in order to be able to get the theory going, okay? And in spite of the fact that it is an assumption, it's a very benign assumption for the very simple reason of the word unknown, okay? I wanted a probability distribution just to get the machinery of probability going, and I'm making no assumptions about the probability distribution. You can pick anyone you want, and I don't even want to know it, okay? So this is very light as assumptions go. Now, when it comes to the Bayesian approach, what you want to do is you want to extend the probabilistic role completely, okay? So that everything is just a big joint probability distribution of all the notions involved. And if you get that going, then you will obviously be able to derive anything in terms of that joint probability distribution. Okay, so when you do this, let's think of something. In the prediction of the heart attack case, remember that we did use probability in order to derive the algorithm for picking a hypothesis. What did we do? We said you have a data set. What is a data set? Bunch of patients with their attributes and whether or not they got a heart attack within a year of getting these measurements. That was the data set. And you were trying to say that I am going to pick the hypothesis, okay, that if this hypothesis truly reflected the probability of getting a heart attack within that time frame, then the probability of getting that data set, which actually took place, would be higher. That was our approach. And we call this the likelihood. Remember? So it's not we are picking the highest probability hypothesis. We don't have the luxury to do that for a reason that will become clear. We are picking the hypothesis that will make the data that actually happened highest possible probability, maximum likelihood. So we already used the probabilistic approach here. Now, the only difference when you go to the Bayesian approach is that you actually go for the real quantity. The data already happened. Why are we maximizing the probability? Well, if maximize the probability, if what happened is likely given a scenario, then that scenario is likely. That's why you call it likelihood, okay? But a more principled approach would be to actually try to use the probability that this is the correct hypothesis given the data. That is the bottom line. I give you the data, this is given, okay? And you have a bunch of hypotheses. You ask yourself, is it this hypothesis or this hypothesis or this hypothesis that reflect the target function? Well, you look for which one is the most probable to be, and you declare that, okay? And that would be the Bayesian approach. If you go to statistics, there is always a school that loves Bayesian, and there is a school that hates Bayesian. And there is sort of an ongoing struggle between them. And it's funny because you think this is mathematics. People shouldn't, have sort of just, tastes like that. But the problem is that Bayesian depends on some things that I will describe here, and the controversy all comes from that assumption. But it came to the level in statistics where they describe a person as, oh, this is a Bayesian person versus, no, I'm not a Bayesian, okay? It's almost like it was a religion or something, okay? But that's the reality of the field, and you will understand why it evolved into that when I describe the components. Okay. The main component that raises the controversy is the prior. So let's look at what that is. Okay. We want the probability of a hypothesis being the correct target function given the data, okay? And if you want to compute that, and even if you have the model for the noise and the model for the input probability distribution, all of the stuff that we had in the learning diagram is already taken for granted. You still need one more probability distribution in order to complete this, okay? And the way to discover it is just, so let's write it down. This probability, and you apply Bayes' rule, hence the word Bayesian, in order to get this from the quantities we know, okay? So we know this one. We know the probability of the data given that if this hypothesis was faithful description of how people got heart attack, then the probability of getting that data is, you just compute how much noise in each point according to this being f, and you get it, and which we got in logistic regression and resulted in the error measure over there. So that was given, okay? The part that we need that is not given is this one, okay? When you multiply them, you get the joint probability distribution, and when you divide by the probability of D, you get the conditional the other direction which you want, okay? Now, there is no sweat in getting this, because if I have the joint probability distribution, I just integrate out whatever I don't want, and I end up with the marginal. So there is no difficulty in this. And in fact, if your job is to just pick H according to this criteria, then this fellow doesn't matter, because it doesn't depend on H. It scales all of them up or down. So if you are picking between two hypotheses according to this probability, you might as well forget about this and take the numerator as your indicator and pick the one that gives you the bigger numerator, okay? So you think of this as proportional to this, and this is what I'm going to use, okay? Now, this is the mystery quantity, so let's put it down and describe it, okay? What does that mean, okay? It's not conditioned on anything. I'm asking you, here's the hypothesis set, okay? It's a perceptron. It has a bunch of weights. Could you please tell me what is the probability that this particular combination of weights will actually give you the target function, okay? How in the world are you going to know that, okay? So what you are doing here is assuming that there is a probability distribution for that. You are going to put a probability distribution over the hypothesis set, the last component in the diagram that didn't really have a hypothesis, the probability reflecting the statement that this hypothesis is indeed the target function, okay? And any discrepancy between the data set and the hypothesis, which is supposed to be the target function, is attributed to the fact that the data is noisy. The data does not reflect the target function. The data deviates by added noise, okay? So this one is called the prior, okay? Prior because it is your belief about the hypothesis set before you got any data, before. After you got the data, you can modify this and you get the probability of H given the data, okay? That's now more informed. You get the specific data from the target function, and then you are going to zoom in and make a better choice among the hypotheses that you have for which one qualifies as the target, okay? And this one is called the posterior, happens after the fact, okay? Now, if you are given the prior, let's say that I actually give you a problem. I don't know the target function, but I know quite a bit about it in terms of probabilities. And here is the way I'm going to formalize that. I'm going to give you a full probability distribution over the entire hypothesis set that tells you the relative probability of different hypotheses being the correct target function. That's my prior. If you have that, you have the joint probability distribution, And if you have the joint probability distribution, you can answer any question. So that's a very attractive route to follow, okay? You can get anything, okay? And because of that, it's important to look at the prior. That is the center of the idea of a Bayesian approach, okay? So the main point I'm making, the only point I'm making, in fact, in this particular section, is the fact that prior is an assumption. So before I get to that, let me give you an example of a prior to make it concrete, the one I refer to. So let's say that you are having a perceptron. So your perceptron model, what is a perceptron model? Okay, it's hyperplanes in some space, d-dimensional. So I have weights W0 up to WD that tell me the slope and the offset. And this will tell me what is the separating plane. And I'm going to use this as a hypothesis in order to separate some data points generated from a target. And I'm going to assume that the target is there. Let's say even you can take a linear target if you want, and added noise. After you generate the points from that target, you flip the labels of some of the guys according to some noise. Okay, let's say 10% of the points are flipped. So this is your contribution of the noise. Just to have something concrete in your mind to imagine. So you have a perceptron. H is specified by the weights. Yeah, perceptron is, you give it an H because it's a full function, but in reality, you just tell me what the parameters are, and I know what is the function because I know what is the separating plane. Okay. So here is a prior. I suggest a prior, possible prior. The prior now I'm going to give it in terms of the weights. So I'm going to tell you which weights are more likely than others, okay? And what I'm going to try to do, I'm going to try to make the assumption as benign as possible, okay? Because I really don't know. I mean, when I say which weights are more likely than possible, I'm not saying which weights are more likely to come out. I'm asking which weights are likely to actually reflect what the target function is. The target function that we said was unknown. Okay, so I'm making some assumptions. I'm trying to reduce the level of crimes that I'm doing. I'm trying to give you something that, let me try to give you something that is fairly vague, that I am not making a big commitment. Okay, so knowing that for the perceptrons, the magnitude of the weights doesn't matter. If you scale all the W's by any positive number up or down, you get the same surface, right? Because it's just classifying +1 or -1. You care about the signal being positive or negative, okay? So I'm going to take W's in a limited range, and I'm going to take them to be uniform, independently. So each weight is between -1 and +1, independently from the other weight, okay? That is my prior, and my hope in putting that prior is that I didn't make a big assumption, okay? Hope is the operative word here. Okay. So what does that mean? Well, it means that, okay, so if I get the probability distribution over all the weights, then I can see which weights contribute to a particular hypothesis, and then I have the prior over H, which is the one I want. Okay? So I have P of H, the probability of H given F, given nothing. And when I'm given the data, I mix now my prior belief about which hypothesis is the target function according to this, which seems to be completely uniform, and then take the data, and the data will tell me that some guys are more possible than others. If I pick something that will require my interpretation of the noise to say that 90% of the points had to flip in order for this to be the correct target, then this is very unlikely because I flipped with only 10%, and therefore this will get demoted among hypotheses according to the evidence coming from the data. Okay, and you compute the probability of the data given H, and then you multiply them, and you get what you want, which is the posterior, and the posterior is the product, at least proportional to the product of the two. Okay, so this is a concrete example if you want to apply this. Okay, now we make the main statement about the prior, and the main statement is that the prior is indeed an assumption. Okay, so let's look at it. Let me take a very simple case, doesn't have to do with learning in particular, to make the point. Let's say that I take the most neutral prior to describe something unknown. So you have something that is unknown, okay, like a target function. In this case, it would be a number. So I have an unknown number, and all I know about it is that it's between -1 and +1, okay? And someone decides that it will be convenient to have a probability distribution over X, notwithstanding the fact that X is not really probabilistic. I'm not running any experiment and generating X's repeatedly. X is just a number sitting out there that I don't know. I don't know not in a probabilistic sense that it's a random variable. I don't know, it's an unknown parameter. Okay, so you ask yourself, would this be equivalent to X being random in some setting? Can you model this with probability? And invariably people will tell you, okay, you look at this, I don't know what X is, so let me model this using a uniform probability distribution from -1 to +1. Okay? On face value, this looks completely innocent and credible. okay? Because here you didn't make any commitment. It is as likely to be this, as this, as this, as this. This one is unknown. So it seems that you captured what the meaning is, okay? I would like to argue that it doesn't. It actually makes a huge assumption. Now, you are not saying that you don't know X. You're saying that I know that X came from this distribution, okay? So if you know that, here are a bunch of stuff that I know that actually I didn't know here. If you generate a bunch of X's and take their average, the chances are you'll be around 0, okay? If you look at a bunch of X's here and you average, I have no clue what you're going to get. If you do this, I can tell you even not only that the average will be close to 0, I can tell you how close it is in terms of variance, okay? Here, I could be all over the place, okay? So you realize that innocent as this may be, this is a different problem than this one, okay? And if you insist on modeling X as a probability, and you want to capture the statement here exactly without adding any assumptions, okay? You can definitely do that, although it looks much less attractive than this one. This is not equivalent, and if you want the true equivalent in terms of probability of this fellow, this is what you're going to have, okay? So here, X is unknown. Here, X is random, and the probability density function of that happens to be a delta function centered around a point A that I don't know. That would be strictly modeling this. This does not model it, okay? And the fact that people take the liberty of doing that results in many cases in really a huge building based on a false premise, okay? In some cases, you get away with it, but in some cases, you don't, okay? So this is the key point, is that when you put a prior, you are actually making a huge assumption. Think of it this way. We took great pains to say the target function is unknown. It could be anything. I'm not going to make assumptions about it, because in reality, when you are in machine learning, if someone knocks on my door and they say they want to learn a function, I really don't know what the function is, okay? So now you go to your hypothesis set, which you picked out of your hat. I'm going to do the neural networks, or I'm going to use linear, whatever it is, okay? And then you say, now here is the probability that for each of these points, I'm going to specify very specifically the probability that this is exactly the target function, okay? And people do that with great ease, okay? And then build on it, okay? All I'm asking for you to realize is, I'm not saying don't do that. I'm just making the statement, realize that you're making an assumption, and it's a big assumption, okay? So let's see the ramifications of that. If you actually knew the prior, you would be in fantastic shape. Why is that? Because you can compute the posterior for every point in your hypothesis set. For every hypothesis, I know now what is the probability of it given D. Mind you, this is H equal F over the entire space, okay? That is, this is really out of sample. I am taking D, which is in sample, and I'm making a statement about the probability for every hypothesis to be out of sample, okay? I don't worry about regularization and VC bounds, and this is it. You know this, you know the prior, you give the data set, you have a model for it, you can compute this explicitly. And based on this probability distribution, you can get a bunch of stuff. For example, you can pick the most probable hypothesis, okay? And without any dispute, this is the most probable hypothesis. You can even go further. Well, I pick the hypothesis set, and this is the probability that each of them is the target function. And now that I have the evidence from the data, I have a better picture of it, which is the posterior. I can now actually ask myself, I can derive the expected value of H. Because I have, for every H, there is a probability. Instead of picking just the highest probability and sticking with it, why don't I get the benefit of the entire probability distribution, okay? Well, the target function could be this one, could be this one, could be this one with these probabilities. If you want a good estimate of the value of the target function at any point x, why don't you take the value of h of x for every hypothesis in your set, okay? And put them together as expected value because you have the probability distribution, and then you get a very good estimate of that, and you can even get an estimate for the error bar. After you get the estimate, this is my estimate for this, I can tell you what are the chances that I'm wrong. think of the possibilities. I'm predicting the stock market, okay? And I learned using this Bayesian learning, and I have the inputs for today, and I want to predict the output, which is what will happen tomorrow, okay? Now, I can tell you the price movement, what is the expected value of the price movement, very specifically, on that X, which is I care about, and I can also tell you what is the error bar. So if I tell you that the expected value is positive and the error bar is small, then the chances are overwhelming that I will move positive, and I will be putting my money in going in that direction. If the error bar is huge, then I'm not so sure, and I'm not sure it's worthwhile betting on it, okay? So it's, that's a good situation to be in. And also, you can derive anything you can imagine. I mean, you have a joint probability distribution, you can really put any events, and you just plug in and collect the points that constitute that event, and you get the probability, and you have an answer for that. Okay. Now, let me make a statement about the approach so far, okay? We have been struggling with VC bounds and loose bounds, and then we have to use regularization, and we use a heuristic for the regularizer, and then we have to set aside a validation set, and we wonder about the independence of the cross-validation. We really have a tough life, okay? So in this approach, okay, it looks like they are doing much better. All they need to do is plug in the quantities, and they get the answer, and they know that the answer is correct. They don't worry about any of the stuff, okay? So the way I think about it is the following. When you are following this ideology, it's as if you want to have a good life, and this is your approach to getting the good life. First, you rob a bank. Then you live righteously ever after. Well, you can live righteously ever after, you can afford it. The other guys are struggling with this and that, with regularization and whatnot. The problem here, obviously, is the first step, okay? And the first step here is sugar-coated greatly. It's a benign prior, it's just uniform, we didn't do anything, because obviously it's very attractive afterwards, okay? But you are standing on very shaky ground, okay? And you should ask yourself, when is this actually justified, okay? If you do it in general without any justification, then, okay, it's a nice theory built on an assumption that doesn't necessarily hold. On the other hand, it can be very valuable, and it can be justified in basically two cases. One of them is that the prior is valid, and the other one is that the prior is irrelevant. Okay? So what do I mean? Okay. Prior is valid is that for some reason that I really don't know, you put a prior, and this is indeed the probability that a particular hypothesis equals the target function. That is a fact, in which case I concede. Okay? You are doing better than me. I can go with all my approximations and heuristics and this and that, and I'm not going to do nearly as good as you do. Okay? So in this case, this trumps all the cases if you know that the assumption is valid. Okay? So if there are cases where the assumption is valid, I highly recommend that you follow this approach. It may be computationally expensive because, for example, when you get expected value with respect to the posterior in a high-dimensional space, that's not an easy task. On the other hand, since this is the ultimate performance, it may be worth the effort. The prior is irrelevant is a more interesting aspect. So the idea is the following. When you put a prior, if you get more and more data sets, and you look at the posterior, you realize that the posterior is affected largely by the data set and less by the prior. If you start from another prior and another prior and another prior, as long as you don't take extremes, you don't put it to 0 at certain points, you just get something reasonable. Okay? It basically gets factored out as you get more and more data. Okay? And because of that, if you have enough data that the prior doesn't matter, then you can think of the prior not as a conceptual addition, it's just a catalyst for the computation. Okay? And there is a particular approach to this where you think, okay, let me pick a prior just because of its analytic properties. I have no reason whatsoever to believe that this is a valid prior. Okay? But it happens to be that when I have this prior and you give me a data point and I compute the posterior, that computation is easy. Okay? These are called conjugate priors, where you don't have to recompute the posterior as an entire function. You parameterize the thing, and you find that all you need to do is change the parameters when you get new data points. So this is completely valid if you are going to do this enough that by the time you arrive, it didn't matter what you started with. Then what you are really doing, you are putting a system in your computation such that you arrive at the correct result, and it doesn't matter what your assumption was. Okay, that's all I'm going to say. So you can take a full course on Bayesian learning, okay, And the techniques are really wonderful. I'm not doubting any of that, okay? Just be careful where to apply them, because there is an assumption, and the assumption is stronger than it seems to the uninitiated. Okay. Let's move to aggregation methods, okay? So I am talking about aggregation methods, as I mentioned, because they are really sort of useful, and they are not that difficult to understand, okay? So I'll give you the big picture, and then you can sort of pursue different algorithms. So first is, what is aggregation, okay? First, it's a method that applies to all models, as we said. So the idea here is that you combine different solutions, okay? So, let's say that I give a homework problem to the class that requires you to develop machine learning. You develop the machine learning algorithm. You get a final hypothesis. Everyone gets a final hypothesis. And now I want to get the final hypothesis of each of you guys and put it together and combine them into a solution, hopefully better because it got the wisdom of everybody here. That is the idea, okay? So what you have a bunch of hypotheses. I would have called them G as a final hypothesis because that's what they are. They are the outcome from full training. So each of them comes from training on the entire D with certain specifications, okay? But I'm still calling them H because I'm using aggregation, the final hypothesis will really be a combination of those guys. So they remain the H notation, not the final hypothesis, okay? So the picture that goes with that, okay? Here is the system that you got. Here is the system that guy next to you got, etc. So I have all of those guys. So now I want to put them together and get one solution. Very easy concept to have, okay? So one example is the example that I gave. Okay, people already solved it, and I want to combine the solutions. Another one is interesting, and it's particularly interesting for computer vision, okay? In many cases, let's say that you want to detect a face, okay? Now, this is a very complicated task. So you could do very simple detections that are related to being a face. You can try to detect, is there an eye, okay? And you will get it right 51% of the time, 52% of the time, okay? Is there a nose, okay? Are the positions relative to each other? Is the lighting consistent? Whatever, I'm just to put stuff, and it doesn't have to have that great meaning. You can just have simple masks that look at the picture and extract a feature that you think is related to being a face. If you take any single feature and you try to decide whether this is a face based or not, you will do horribly because the error will be huge, okay? Now, if you put them all together and think of them as different ways of putting at it, and then you combine them correctly, then the decision all of a sudden is reliable, okay? This is important in machine vision because in computer vision, because in computer vision, the computation is a big deal. You need to do things quickly because you're trying to be either real time or close to real time, okay? So using very simple features, as they're called in this case, and then combining them, then that is a good application for it. Okay. So let's talk about what is combining. Well, combining is very simple. I mean, there are many ways of combining. The most common is that if it's a regression problem, these are guys give you a real number. Take an average, okay? If you are doing classification, so everybody is deciding yes or no, take a vote, okay? Could be weighted average and weighted vote, but that's basically the essence of it. And there are other ways of combining them, okay? Now, there are many names for aggregation. You can see it as ensemble learning. Boosting is definitely one of them. Mixture of experts is another. There are lots of methods that belong to that category. Okay. Now, let me make the point that it is different to do aggregation than to just do a two-layer learning. Okay, so what do I mean by that? If you have a two-layer model, so there are a bunch of features followed by one. You have seen that already, like a neural network. Neurons in the hidden layer feeding into the output, and you are trying to learn. Okay. The learning is joint. You learn all of the units at once. So you look at this. Let me magnify it. Okay. These are your units. What your learning algorithm does, it takes the data and simultaneously adjusts all of these guys in order to get the right solution. This could be backpropagation, for example. Okay. And in that case, any one of them is not necessarily trying to replicate the function. Okay. It's just trying to contribute positively to the function. So finally, in the final layer, you could be taking the difference between these two units, and that is the important thing that affects you in the output, okay? So the guys here are not trying to get it right, are just trying to be sort of good soldiers and good features in that. And the reason you do that, because you are doing it all at once, and you're trying to minimize the error, so whatever combination happens, happens, okay? So this is what we have done before, okay? Now, in the case of aggregation, the units learn independently, that each one learns as if it was the only unit. Okay, so you are actually trying to learn the function, and then you combine them. So you look at this picture, okay? And in this case, the learning algorithm looks at one at a time, okay? Maybe it's different learning algorithm, but at least it's considered one at a time, and then gets you what that is. And this guy is actually trying to replicate the function. And this one is also trying to replicate the function, okay, etc. And finally, when you have all of these guys that are trying to replicate the function, you combine them and you get the output. So that is the difference. Okay. Now, there are two types of aggregation, okay? And I'm going to call them certain names for lack of a better word, but they are really different categories, and I wanted to emphasize this point. One of them I call after the fact, okay? What does that mean? It means that you already have solutions, okay? For example, remember the Netflix guys? Okay, so you have the crowdsourcing, and you let the problem out. Everybody tries their hard, and then gets a solution. Now you would like to combine these solutions. These solutions exist. They were developed with a view to performance individually. Nobody was thinking about putting them together, okay? If you are thinking about putting them together, you may have other considerations. For example, you may decide, okay, this was going to go into a blend, which is the word that goes with it, okay? And therefore, I'd better get something that is different from what the other guys are having in order to be able to contribute. Because there are other considerations, okay? But no, in this case, you just get the solutions, and then you combine them. So that's one approach. The other one, which is the boosting approach, is, I'm calling it before the fact to contrast, which is the fact that you are developing the solutions with a view to the fact that they will be blended, okay? So you get one guy, and then when you go to the other guy, you are trying to develop a guy that will blend well with the first guy, etc. Okay? So you are not trying to get it to perform well in its own right. You are trying to make it a good part of a blend, okay? And we saw an example of that in one of the Q&A sessions, which was a question of bagging, where I give you the data set, and let's say that I want to give the class the problem, but I want to combine at the end, okay? And they are going to work independently. So I want to do something to make sure that they are fairly independent. So what I do, I resample D and give everybody a different sample from D, a bootstrap sample. So because of that, I introduce some independence in the information you are getting. So when you get something, I am hoping that when I put them together, I will get the benefit of that independence, okay? So in this case, this is what I'm doing for the case of bagging. I'm actually giving every one of them a different data set, but it's independent from the other guys, and then I'm going to combine what they have. Okay. Now this leads to the boosting algorithms, which are very successful algorithms. And the idea here is that instead of leaving the decorrelation to chance, I am going to enforce it, okay? So I am building one hypothesis and the next one, and I am making sure that whatever I am getting in the new hypothesis is novel, was not covered by the previous guys, okay? And that obviously improves my chances of getting a good mix, okay? So what you do, you create the hypothesis sequentially. So you do 1, 2, 3, 4, and then given the 4 that you have so far, what is the best fifth that I can add to the mix, okay? And you make it good by making it decorrelated with the other guys. So the picture here is rather interesting. So it's not quite independent, but it's not as bad as doing all of them at once. What you do, you have already done those. So this is a recursive procedure, okay? Now you read off from these and you realize how they perform. And based on that, you do something such that the data set you pass on to the new guy makes it develop something that is fairly independent from the previous guys. And now this is frozen, and it contributes here, and then this guy is trying to be independent of all the previous guys. So every time you have one, you get something new, okay? Therefore, by the time you put them in the mix, you get something interesting, okay? So this is the idea. And the way to do the independent is rather interesting. Let's say that so far I have 60% correct and 40% wrong. That's what I have achieved using the first few guys, okay? So when I put them together, that's what I get. 60% and 40% means that 60% of the examples I got right if it's classification, okay? And 40% I got wrong, okay? So here is an idea to make the new guy fairly independent of those guys. Let's say that I emphasize the guys that I did badly on. I give them bigger weights in the training. and de-emphasize the guys that I got right, okay? Such that as far as the new distribution is concerned, the new emphasis I have, it looks that what I have so far is 50-50. It's random, okay? So what I have is not random because it deals with that training set as it is. But if I give it different weights, and I ask myself, what is the weighted error now? And the weighted error is 50%, it means that it's, as far as the previous guys is concerned, it's as if it's a random guess. So if I take that distribution and learn on it and get something better than 50%, then the new guy I am getting is adding value to what I had before. This is the general principle. And when you plug in this, you get a very specific algorithm. You do this recursively, and you get not only how you emphasize the examples given the old ones, you also give derive the different weights of the mix. So some of the guys will be successful in training, and some of them will not be successful, and you are going to have weights according to that. The most famous algorithm here, which is a very specific prescription for how you do the emphasis and how you do the weighting, is called adaptive boosting, AdaBoost, and it is the one that is used in the computer vision example that I gave. And indeed, in that case, what you are doing, you are, instead of working with just error, trying to make it 50-50, you are actually working with something similar to the margin that we had before. Remember, when we had the support vector machines, we weren't settling for getting it right. We want to get it right with a margin of safety. So the AdaBoost algorithm defines a cost function that has to do with violation of a margin, okay? And then tries to improve that margin as you go. And the weights, both for emphasizing the examples and for picking the combination of the hypothesis you have, are with a view to maximizing that margin. And it's a very successful algorithm in practice. Okay. Now let me, the final technical slide, talk about the blending after the fact, because it was applied to Netflix with great success. And I want your attention because I'm going to give you a puzzle, last puzzle of the course, I guess. Okay, so here is the deal. Now, I don't have the benefit of decorrelation or anything. I don't have a choice. I just give the data to people. They came up with solutions. And now we want to put them together. Think of yourself as the last month of Netflix, and you want to win. And the other teams are getting together and getting good results. So you look for other guys that look promising. They have good solutions. They already have the solutions. They are not going to ask them to, let's redo the whole thing with a view to record. There's no time, okay? So what you want to do is just you want to take their solutions and put them together and get the answer, okay? So you want this, and your plan is, okay, let me do this. It's a regression problem. You are trying to get a rating. And therefore, what I'm going to do, I'm going to combine the solutions that I have using some coefficients from t equals 1 to capital T. And now my job is to pick the alphas optimally. The best combination for the solution so that I get a good performance. Now, you can think of this as a very simple training at a higher level, okay? Now, you take the solutions as if they were the inputs, okay? And you are trying to predict the output, which is the same output. So what you are going to do, you are going to have a principal choice of alphas using now not a training set, not a test set, not a validation set, but an aggregation set. So you set aside some points that were not used in the development of these guys, okay? And then you use those just to decide what are the best coefficients you have for these solutions, such that the error on that aggregation set is the best possible, okay? Now, if you do this, guess if you use mean square error, what will your algorithm be for choosing alphas? It's the good old pseudo inverse again. You do this and you minimize it. Now, it's important to realize here that I really need a clean set. If I use the training set that these guys used, okay, then the guy that got the best training set, the training error, will have a big weight because, okay, and obviously that's a problem because we know that having a big, small training error is not indicative. But if these guys are frozen and I take a fresh set and then I get the combination, it's completely valid, and then I get those guys and get the solution, okay? So now comes an interesting thing. Let's say that I do this in class, which I actually did, okay? There was a, time we had the Netflix data, and people will come up with solutions with a view to aggregation. That's when the competition was still alive. Okay, so people came up with a solution. So now I want to combine them. Okay, so can you imagine you work on this, you have your solution. Your solution is supposed to predict the rating, okay, and the other guy is predicting the rating, and then I am putting him in. So you think, okay, maybe the guy that has a big alpha has a good solution because its solution is affecting the output a lot. Okay, Now, can you imagine what happens if your alpha is negative? You worked hard, you got a solution, okay? And then when you put that solution together with the best solutions, the best possible outcome we can get is by subtracting your solution from the total, okay? That was completely devastating to people, but please don't sort of lose your self-esteem because of this. The size of the weights is not the criteria, or the sign of the weights is not the criteria for your solution being valuable. Because it could be that you are so correlated with other solutions that what the system is trying to do is trying to combine those in order to get the signal part right and eliminate the noise. So depending on the noise on your solution, you could be negative. You are contributing to that mix. So although it looks on face value that negative, oh my God, if I did nothing, I would have gotten a weight 0, and now I have a weight. No, that's not the case. So the question is, how do you evaluate which of those solutions is the most valuable in the blend? I had that practical problem because I wanted to reward people, and I don't want people, when I give this problem, everybody is trying to do the same thing because it gives them the best performance, okay? So I would like to reward someone who did something adventurous and therefore got a different angle on it and therefore contributed to the blend, okay? Whereas the other guys who are all doing the same thing, everybody will get a small share, so it's not a big deal, okay? So I wanted to have an objective criteria for doing that. What would you do in order to evaluate that? By the way, this actually was used in the competition as well when eventually there was one team that decided that to have an open announcement, anybody can join. Give us your solution, and we will see how useful it is, and then we will give you stocks in the prize according to how much you contributed, and it will open. And actually, that team ended up in second place. Okay, so it's not like a bad idea. Okay, so the idea here is that if you really want to know the value of a particular hypothesis, here's what you do. You take it out. You evaluate all without your solution. You get a performance. And then you evaluate with your solution, and you get another performance. The difference is the contribution of your solution. So one of the ramifications of that is that if two people are doing identically the same thing, then obviously each of them is useless. Because when you take it out, the other guy will hold the day, okay? But those guys who did something completely fringy, although I ask you, what is your performance? Oh, I got 6% towards 10%. And what is your performance? I got only 3.5%, okay? But then when I look at the contribution to the final thing, when I put them together, I get a total performance, let's say, of 8%, okay? If I take the 3.5% out, the 8% drops to 7.5%, okay? So they contribute 0.5%, okay? If I take the guy who had 6% and take it out, the 8% goes to 7.95. Who cares, okay? So this was the way in order to be able to reward your actual contribution to a mix. Okay, now, there will be no Q&A session today, but I will be happy to answer questions on the forum. What I'm going to do now, I'm going to do acknowledgements for people who contributed to the course before I close on a personal note. The first acknowledgement goes to my colleagues, Professor Malik Magdon Ismail and Professor Xuan Tien Lin. Okay? All I can say is that they are as responsible for the content of this course as I am. Enough said. Now, I'd like to acknowledge the course staff. There are many people who helped. I am singling out the people who contributed the most. And Carlos, Ron, Kostis, and Doris have contributed to everything you can imagine about the course, from suggestions about the format, even getting the right slide system, designing the homeworks, writing the registration and online system from scratch, everything you can imagine. And they filled in to other tasks when it was needed, and they ended up working far more than they are paid for. So I'm really grateful to them. And the head TA, who is Carlos, happens to be familiar to you. You heard his voice in every lecture. He is the voice of the Q&A session. And I suspect that people are curious to see what the guy looks like. They heard his voice, okay? So let me ask Carlos to come to the podium and say hello to the online audience. Okay, so
hi. So you know my voice, now you know my face.
Okay, so you are exempt from the Q&A session today. Fair enough. Thank you so much.
It's an honor to work with Yasser. It's really great to work with him. So thank you,
so
Yasser.
much. Very good. Thank you. Okay. Now, most of the people have seen this course, and by everybody after that will see this course through the tapes, okay? And the medium that resulted in those tapes are the AMT staff, Leslie Maxwell being the director. And I would like to acknowledge them in very passionate terms. They have done an enormous job. It was great amount of work for them. And they are all here, obviously, with the cameras and that. And I'm really grateful to their contribution. I'm also grateful to the computing support staff and Rich in particular, not only because of providing the infrastructure for having this course, but also for supporting the idea of the course very early before we even raised the money. So we had a head start on this, and we started talking to people and doing that, and we weren't sure even that it will happen. So I appreciate the fact that there was confidence that this might be a good idea in order to put that to begin with. Okay. Now, this course cost money, and I was insistent, and Caltech was insistent, that this will be perpetually free for everyone. That was the whole idea. We wanted to give a Caltech quality course to anybody who has the discipline to follow such course without costing them a penny, okay? And we succeeded in that, and in order to succeed in that, you actually need the money. If we didn't raise the money, this would not have happened. And I'd like to acknowledge the sources of the money and the people who drove the money raising: the Information Science and Technology Initiative, the Engineering and Applied Science Division, and the Provost's Office. Mathieu, in particular, took the lead on raising the money, in getting the publicity. He just sort of took an interest in this and was incredibly invaluable in getting this going. And at the division, both Aris and Manny were very helpful and supportive. And believe me, if you do something that intensive, you need the support of everybody. Otherwise, you lose heart in the middle. And that was very instrumental in getting this going. And at the Provost's Office, both Ed and Melanie reached for the educational funds and got the money, so we didn't have to worry about it. So it's not only financial support, it's also moral support and confidence that this will be something good. Now, there are many people that I will have forgotten to acknowledge, so I'm going to give a general acknowledgement, and I apologize for any particular person that contributed and I forgot to give them their sort of due reward. Okay. The TAs, other than the ones I mentioned, have contributed greatly, and they took a load off my agenda by answering questions to the students and taking care of the homeworks. And there are many staff members at the division level and at the departmental level who helped in all kinds of ways. The Caltech alumni were absolutely great. I got an incredible support from the Caltech alumni, who are genuinely a family spread around the world. And the Alumni Association that helped get the word out was very instrumental in getting the publicity right. And I had incredible support from colleagues all over the world, okay? I usually don't like my email because 70% is spam and 20% are scams and then 10% are relevant, okay? But it was worth going through all of this in order to hear the wonderful words of support that are getting from the four corners of the world. Okay. Now, on a personal note, allow me to dedicate the course to the best friend I have ever had. Well, I learned a lot from her, and learning is precious. And my hope is that this course was a positive learning experience for everyone, okay? And in particular, I thank my Caltech students for really putting up with the inconvenience of cameras, regimented lecture format, and whatnot, in order to share this learning experience with the whole world. Thank you.